Hello everyone, welcome back to my channel. In this part 4, we are gonna continue solving the remaining subproblems. Let's get started. Now let's continue with the rest. And it says we want to obtain J through dehydration of G in acidic environment, but we get L instead of J. Again, long sentences, a lot of information. It's not helpful, so we need to put in a diagram form. So I go back to the part of the synthesis where we had J and G. And this is J. And what happened here is that they wanted to try to get compound J, this one, from G using acidic environment. So I'm just going to show it as hydrogen plus, but it didn't work. Instead, when you take G in acidic environment, you got L. Now we need to draw a structure for L. So we have compound G, which is secondary alcohol, and we need to find out what could happen here. What would be the interaction of alcohol, a secondary alcohol, with a proton? So now we have to think about potential interaction. Also, we have to keep in mind that we are trying to have elimination reaction. Let's take a look at the original reaction from G to J. So what they did here is actually elimination, but as we know, we have two types of elimination, E1 and E2. Here, what happened was E2 elimination. So what they did was actually not from G to J, but from H to J. So when they get H, which is the similar structure, but much better leaving group, what they did was they took a base and there's a beta hydrogen. So it comes here, this goes here, and O acetate leaves. So this is called E2 elimination, and it gave a product. But now when you are using hydrogen plus, we are not going to have E2 elimination. We are going to have E1 elimination. So OH is going to attack to hydrogen plus, and then water will leave. So this is going to be the first step, which we call as unimolecular reaction. It's going to attack here. It's going to become OH2 plus, and then it will leave as water molecule. So we are going to have a positive charge here. And ideally, because we want to get J, what we can do is this, actually the water that leaves can act as a base and remove a proton from here through this reaction, and we can get our J that we actually desire to obtain, but that doesn't happen because of carbocation rearrangement. So as you can see, when H2O leaves from the original alcohol G, we get a secondary carbocation. But there's a chance for a shift so that we can get a tertiary carbocation. And this is something that's impossible to avoid. So if carbocation rearrangement can occur, they do occur. There is no way to prevent that from happening because it's intermediate, right? It's a carbocation intermediate. It will see that, oh, there is something more stable. So always tertiary third degree carbocation is more stable than the secondary, which is more stable than primary, which is more stable than methyl. So the reason why we are having this trend is because when you have tertiary carbocation, you have a positive charge surrounded by, let's say this is a carbon and it's surrounded by, let's say, 3 alkyl groups. And this is the effect we call as hyperconjugation. So the bonds that are neighboring to this positive charge, they have some electron density and they are donating this electron density through hyperconjugation. So because this carbon plus has empty p orbital, it's an electron deficient. So it wants to get more electrons from electron density to itself so that it can be stabilized better. So that's why when you have tertiary carbocation, you have more neighboring bonds around positive charge, around empty p orbital. So which means you have more chance to stabilize it. So that's why tertiary is always going to be more stable than secondary, which in turn is more stable than primary. So this effect, this trend is explained by hyperconjugation. So it's impossible to avoid this from happening. Intermediate will always try to go to another intermediate, which is more stable. In this case, secondary carbocation will try to move toward a tertiary carbocation, and this is called methyl shift because we are shifting a methyl group from one carbon to another, and by doing so, we are also shifting the position of positive charge from this carbon to this carbon. Our goal here is to get tertiary carbocation, and we get our tertiary carbocation, and then we do elimination here. So there's hydrogen, and again, water acts as a base. This attacks here, and this moves here. So this is E1 elimination after carbocation rearrangement. So this is gonna be the structure of L. Now we are done with question number 1 and question number 2. Let's go. This is the next part, and it's really interesting. So we have hydrocarbon 1, an exothermic reaction with two different geometric isomers M and N at 20 degrees. We have two compounds in the case of reaction with M and a single compound Q in the second. So we need to write structural formulas for M and Q, and we are given another fact that O, P, Q all have molecular formula with 9 carbon atoms, 10 hydrogens, and 4 oxygens. First thing first, again, we have a bunch of words, sentences, we don't like them. So what we need to do first is to convert them into diagram form so that whenever we have any information that we need to look up, we don't have to read the entire sentences again. Just the diagram chart form is always easy. So we just convert it. We have hydrocarbon 1, M reacting with M to give O plus P. With N, it gives Q. And all of them have the molecular formula given. And maybe we can also add 20 degrees. Maybe at this point, it's not important. But we can just write it here as, okay, these reactions have been carried out at 20 degrees. And since we are given molecular formula and this M and N are geometric isomers, and this is diene, and previously we have done some Diels-Alder reaction or pericyclic reaction. So we are assuming that it's just, we don't have anything else formed, right? So we have just hydrocarbon 1 combined with M to get O or P, O plus P, or for example, hydrocarbon 1 combined with N to give Q. So we can do this molecular formula subtraction thing. We know the molecular formula of OPQ. Let's just use the second reaction, hydrocarbon 1 plus N to give you Q. Q has the molecular formula C9H10O4, and hydrocarbon 1 has the formula C5H6. It's just a 5 carbon, 6 hydrogen. So we can just subtract it to get this molecular formula of M and N. It's same because M and N are geometric isomers, so they obviously have the same molecular formula. So this thing, does it work every time? No. But in this specific case, because we know that first, when you look at this compound, you know that it doesn't have a lot of functional groups. We are not expecting crazy Grignard reaction, alkene metathesis, Witting olefination, those kind of reactions. We do not expect here. Or aldol condensation, Claisen condensation. We don't expect any of this, right? Because that's not a crazy molecule with a lot of functional groups. It's just the diene. And M and N are geometric isomers. So what is geometric isomers? It's actually cis and trans, right? Usually that's the most common example of geometric isomerism, cis plus trans. So what does it mean? When do we have cis and trans? We only have that in alkene. So M and N are alkene, and this one is diene. So the only possible reaction here is obviously Diels-Alder reaction of this type. We have diene here, alkene here. They react with each other. They give a cycle like this. So as you can see, you can just add up their molecular formula. For example, in this case, it's C4H1, 2, 3, 4, 5, 6, H6 plus this one is C2H4. When you add them up, it's just C6H10. So you literally add them up because there's nothing else, right? And according to the law of conservation of masses, we have to keep the same number of atoms on the both sides. Since we do not have any byproduct, we can literally add the molecular formulas of the reagents to get the molecular formula of the product. So here we have the molecular formula of the product. We have the molecular formula for one of the reagent, which is C5H6. So we can easily subtract. So my point here is that it doesn't work every single time, but in this specific case, when we are sure that our reaction is pure combination reaction with no additional side product. So by applying this chain of salts, we find out that the molecular formula for M and N is C4H4O4. So based on that, we can find HDI. So for 4 carbon atoms, maximum number of hydrogens we can have is 4 multiplied by 2 plus 2, which is 10, but we only have 4. So difference divided by 2, it gives us 3. So it has HDI of 3, which could be many things like 1 ring, 2 pi bonds, or 3 pi bonds. We don't know. It could happen. There are a lot of possibilities. So let's just put everything together. What we know about M and N. They are geometric isomers. They both have the molecular formula like this. They have 4 oxygens, 3 HDI, and they should have alkene functional group for Diels-Alder reaction. Because it's going to be really easy to construct the structure for this molecule because we only have 4 carbon atoms. If you have more carbon atoms, it's going to be really difficult, right? But we only have 4, and we already know that 2 of them should be like this because we need to have alkene functional group, right? in order to react with this diene according to BSR the reaction. So we have our 2 carbon atoms and we also have 4 oxygens. So I am actually assuming that this compound is symmetric for now. So I can put 1 carbon here. It's just an assumption, right? I'm not 100% sure. I'm just saying because that makes things easier. Now I have to think about C2H2O2 and I have to double it, right? That makes things easier. Probably the person who made, or people who made this question, they also are aware of the fact that among all possibilities, you cannot just randomly construct a structure for any molecular formula with 4 carbon, 4 oxygen, 4 hydrogen. It's impossible. So it's better be symmetric. Let's put it this way. That should be your first assumption, because otherwise it's gonna be a really time-consuming task just to construct the structure from a molecular formula. So I have to assume basically that this is symmetric. And I also have 3 HDI. I also used one of them here. So I am left with 2 HDI. So since I am using it symmetrical, so I should have 1 HDI in each side. 1 HDI here. When I say 1 HDI, I mean a moiety that contributes to HDI, which could be a ring or a pi bond. Because I already have double bond in between, so this is already 1 HDI. So I need 1 HDI in each side. So by having these, everything together, and I also have 4 oxygens, so 2 oxygens should be here. And can I have a ring here? Because I also have just 2 carbons here, so 2 carbons here. I'm just putting it here and 2 hydrogens here. So I hope it makes sense, right? So I have to use C2H2O2 on this side and 2 carbons here. I have to connect them this somehow. I hope it makes perfect sense. We are getting there. And then this should be connected in 1 HDI fashion, right? They cannot make any cycle. If that is the cycle, then you have to make oxygen bond, which is really unstable in 4-membered ring. And in general, 4-membered ring is really unstable. So I don't think we can have any ring with this small number of atoms. So it's highly probable that we have a double bond. Oh, we have only 1 carbon atom. Sorry. So these carbon atoms are actually within this. So within this double bond. So I only need actually 1 carbon atom in each side. Sorry about that. And so 1 carbon, 2 oxygen, and 2 hydrogen. So what I can do here is I can have COOH, which is carboxylic acid group. And actually it makes perfect sense. If I have carboxylic acid group here and carboxylic acid group here, and one of the hydrogen will be here and another hydrogen obviously will be in the double bond. So that actually satisfies our requirement. And then I can also have geometric isomers in this case. So this structure for M and N makes perfect sense. Now that we have found the structure of M and N and it makes perfect sense, it fits all pieces of information that are given. They are geometric isomers. These are cis, COOH and COOH are on the same side. So these are cis and this is trans. Now that we have 2 geometric isomers for M and N respectively, we can find out the structure of other compounds. And I say respectively, actually it's wrong because I don't know which one is which. I don't know if, or this is M. This we will be able to find out if we consider the structure of O, P, and Q, or the information that one of them yields 2, for example, M gives 2 of them, but N only gives 1. So actually this is enough for us to find out which is which. So let's go back. So we have this scheme, hydrocarbon 1 reacting with M and N, M gives O plus P, N gives Q, and I am putting everything together. This is my hydrocarbon 1. With M, which is cis isomer, I get 2 products. With N, which is trans isomer, I only get 1 product. So why this is the case? Because as you can see with cis isomer, I have this COOH group. They are both endo. So what does endo mean? It means if you consider this similar to cyclohexane conformation, every time it has axial and equatorial, you can think of it like this, or maybe just up and down, or you can just think of it as this bridge. You have this bridge here, we call it as a smaller bridge, and you have another bridge like larger bridge. So you can also think of it as a position that is opposite to small bridge. You can think of it like this. So endo conformation is where your substituents, your groups are on the same side, are cis to a large bridge. And exo is when you have those groups trans to each other. So if you can think of it like this, if you want to see this bond, you see like this. So this goes up, these groups goes up, but this goes down. So your bridge, your larger bridge, and your compounds are trans to each other. But in this case, they are on the same side. So this bridge and these compounds are on the same side. They are cis to each other. So we call this as endo. So when you use cis isomer, there's a chance that both of them are endo or both of them are exo. So that's why one of them is going to be O and one of them is going to P, and that makes M as cis isomer. So if you remember, we had cis and we have trans, but we didn't know which one is N and which one is M. So but now we know that cis isomer should be M because cis isomer is the one that gives two products. With trans isomer, you get just one of them exo and one of them endo. It doesn't matter. You don't have another case because if you just put here endo and here exo like the opposite, it's still the same. So you don't have two different compounds. So when you use trans isomer, you only get one. So I see here, I take a look at here, I get one compound here, Q, so that makes N as a trans isomer, but I get O and P here, which means two compounds here, that makes M as cis isomer. So I was able to differentiate between cis and trans, and I was able to label them as M and N respectively. So now Q is easy as well because which is same as here, 1 reacts with N to give you Q. So this part is easy. And in here, they actually gave us information about relative distribution of the products. It says O is 85% and P is 15%. So here, endo transition state is more stable than exo transition state. So when we make this compound, when they react, we have a transition state and we are conducting this reaction in kinetic condition. If you remember, it was 20 degrees. We don't use any high temperatures or something like that. So since we are using low temperature, we favor the formation of kinetic product. I will come back to this again, kinetic product, thermodynamic product. So the one that forms faster is going to be major product here. So here, endo transition state is more stable than exo transition state. So that means O is going to form much faster and that's going to be major product. So I will come back to this again. And also I want you to take a note that I didn't say endo product is more stable than exo product. I am just saying endo transition state is more stable than that. So I will come back to this again because question number 4 is directly related to this. But here O is going to be both endo because O is the major product, 85%, and P is the one that's going to have both groups in exo position because it's minor product, just 15%. We are done with question number 3, and lastly, they ask us to draw a qualitative energy diagram for the reaction of hydrocarbon 1 with M, given the fact that it is thermodynamically less stable than P. So we already know this, right? So we have hydrocarbon 1 reacting with M, which is cis isomer, and there's are two possibilities, compound O and compound P. In O, we have both in endo, and in P, we have both exo. And they told us that O is thermodynamically less stable. This is given fact. But O is 85%. How is this possible? If O is less stable than product P from thermodynamics perspective, then why we are not getting P as our major product, right? Why O is predominating in the reaction product mixture? The reason is because it's a kinetic product and we are conducting reaction under kinetic conditions, low temperature for 20 degrees, right? So yes, it is thermodynamically less stable, but it forms faster. So that's why it's kinetic product. And then we are gonna have a energy diagram like this. This is our starting materials, I plus M. And if you see here, for O, which is a blue line, it has lower activation energy because it has lower transition state, even though P is more stable at the end. P has a lower energy. But it depends on how we are carrying out the reaction. Are we carrying out it in kinetic conditions, or are we conducting it under thermodynamic conditions, for example, high temperatures? So this directly affects the product distribution. So in this case, why compound O is a kinetic product, let's explain that one. So when we form Diels-Halder reaction, when we are writing mechanism, so what happens here is that we have our diene and we have our alkene, right? It has COOA and COOH. So when we try to form cyclohexene ring, we are going through this transition state that looks like this, but here, instead of full bonds, we are having partial bonds, right? We are forming this bond. Okay, I will just show it like that here. And we are forming our pi bond here as well. So this is the transition state that leads to O. And as you can see, I am having this in endo position. So I'm going to write it in an open form. So this is electron withdrawing group. And I am forming a pi bond here. So there's a favorable interaction between developing pi bonds and electron withdrawing group. There's a favorable interaction here. and that stabilizes transition energy. So when you stabilize transition state, energy of transition state is gonna go down, which is gonna make activation energy lower, and that directly increases the reaction rate. So that's why it's called kinetics, because kinetics is the study of reaction rates. Anything that forms faster in certain conditions, we call it kinetic product. So this is the reason why endo-transition state is more stable than exotransition state. So when you see this graph, this O is both endo, right? Endo. And the transition state here is obviously gonna be lower energy transition state because of favorable interaction. So we will have this gap here between exo transition state and endo transition state, and that will make product all faster. Because we are only carrying out reaction under 20 degrees, we are not supplying a lot of heat or something like this, so obviously the product that forms faster is going to be major product. That explains full thermodynamic profile of the reaction. And if you wonder why, even though transition state for endo product is lower in energy, why at the end of the day we have O product? The reason is, if you see the structure for O, you will see that the COOH groups are cis to this large bridge. So there's a steric interaction here. So just this is a similar reasoning to why cis alkenes and trans alkenes, if you compare them, trans alkenes are always stable. Why is that? Because in cis alkene, your groups are on the same side, so there is some steric interaction. So you prefer them to be located from each other as far as possible. So that's a similar reason here, right? So even though they're electron withdrawing, they're stabilizing transition state energy, but at the end of the day, they are cis to large bridge, so that destabilize this overall structure at the end. So that's why P as a product is more stable from thermodynamics perspective. But since we are not employing thermodynamic conditions like elevated temperatures, we have O as our major product. Now all parts are complete. We are done with our first problem. If you want the original problem and the full step-by-step solution, just check the forum in the description below and I will email them to you. Thanks for watching.